Hey guys, welcome back to my channel. Today we're going to be looking at GCSE Chemistry, Topic 7, Organic Chemistry. Now I know it says AQA, but a lot of this content will be useful for other exam boards as well, so do not panic. But before we jump in, I will be uploading a few more. We only got a few topics left of GCSE Chemistry, and then I will be jumping into A-level Chemistry. So, for those of you doing the exam this year and maybe wanting to do A-level Chemistry next year, then, go give me a subscribe. Feel free to like this video, and if you have any questions at all, please feel free to comment them below, either myself or your fellow students will answer it for you, so whoever gets there first. But let's just jump straight in. My words are muddled already. Let's jump straight into organic chemistry. So firstly, looking at carbon compounds as fuel and feedstock. So crude oil is a finite resource found in rocks made from the remainders of an ancient biomass consisting mainly of plankton that were buried in mud. It's a mixture of a very large number of compounds which are separated by physical methods. So the key example that you guys will need to know is distillation, which we will discuss in a little bit. Most of the compounds in crude oil consist of molecules made up of hydrogen and carbon only, known as hydrocarbons. Most of these are saturated, so these are called alkanes. And you can see a little picture here. This is kind of what your most basic alkane will look like. And hydrocarbon alkanes have a general formula of CnH2n plus 2. The first four alkanes are methane, ethane, propane, and butane. Now, the key for this is really to essentially remember the first bit of those words, so meth, eth, prop, and but, because it's the ending that will change depending on the structure. But again, we will discuss that a little bit further. We'll see that later on in the presentation. So looking at fractional distillation. So this is a method of separating crude oil. The oil is heated in the fractionating column, and the oil evaporates and condenses at various temperatures. So this is the key to actually how they become separated, because of the fact that they will boil or heat and separate at different temperatures, so they will separate off from each other. So this is where they become separated into fractions, each containing molecules with a similar number of carbon atoms. The vaporized oil evaporates and rises up the column, and various fractions are constantly tapped off at different levels where they condense. The fractions can be processed to produce fuels and feedstock for the petrochemical industry. So examples of fuel, so petrol, diesel, kerosene, how we run our cars is kind of done through this. And the petrochemical industry develops solvents, lubricants, detergents, etc. The vast array of natural and synthetic carbon compounds occur due to the ability of carbon atoms to form families of similar compounds. Then some properties of hydrocarbons. So this depends on the size of their molecules and how they can be used. These properties influence how they can be used as fuels. The shorter the molecule, the less viscous it is, aka thick. It vaporizes at a lower temperature and has a lower boiling point, and it is more flammable. So hydrocarbons are burnt, so they could be used as fuel, and the kind of key reaction is hydrocarbon turns into carbon dioxide and water, and the hydrogen and carbon are oxidized in this reaction. So hydrocarbons can be cracked to produce smaller, more useful molecules. This involves heating to vaporize the hydrocarbons. The processes are passing them over a hot catalyst, so this is called catalytic cracking. Or you have an alternative, which is mixing the hydrocarbon with steam and heated to a very high temperature so that thermal decomposition can take place, also known as steam cracking. The products of cracking include alkanes, but also unsaturated hydrocarbons. So obviously alkanes are saturated, and now we have unsaturated hydrocarbons, which are called alkenes, with a general formula of CnH2n, and have at least one double carbon-carbon bond, which you can see here in the little diagram. The first four alkenes are ethene, propene, butene, and pentene. Again, you can see what I mean there. Then alkenes react with bromine water, turning it from orange to colourless. Alkanes do not. The double bond makes them more reactive and used for producing producing chemicals such as polymers. Some products from cracking are useful as fuels as they have shorter chains than the alkanes we started off with, so are more flammable. Now looking at the reactions of alkenes and alcohols, so alkenes are unsaturated because they contain 2 fewer hydrogen than the alkane, and obviously these have a functional group of carbon double bonded to another carbon atom. They react with oxygen in combustion reactions in the same way as other hydrocarbons, but they tend to burn in air with smoky flames because of incomplete combustion. So when it comes to incomplete combustion, this is where carbon or carbon monoxide is formed. They also react with hydrogen, water, and the halogens by the addition of atoms across the carbon-carbon double bond, so that the double bond becomes a single carbon-carbon bond. So you can kind of see in the table here how they react. So essentially what they look like as alkenes and how they then look as alkanes once they've reacted with bromine, water, and hydrogen. The key here is that when looking at the bromine one in the top example, this would be the exact same for chlorine and iodine as well. It will look exactly like that. In each reaction with hydrogen, water, and halogen, so every reaction works the same for all alkenes. The double bond between the carbon atoms is broken to form a single bond. The compound added splits into 2 groups, and the 2 groups are added to the 2 different carbon atoms in the double bond. So H2 splits into 2 H's, H2O splits into H and OH, and Br2 splits into 2 Brs. Then alcohols contain the functional group OH, and the first 4 alcohols are methanol, ethanol, propanol, and butanol. Reactions for this, so these burn in air producing carbon dioxide and water. They dissolve in water to form a neutral solution, so a pH of 7. They react with a sodium to produce hydrogen and a salt, and react with oxidizing agents to form carboxylic acids. Methanol can be used for chemical feedstock in antifreeze and to also make biodiesel. Then ethanol is the main alcohol in alcoholic drinks that I know a lot of you do not drink. Used as a solvent and fuel. It's produced by the fermentation of sugar with yeast using renewable sources. And in terms of the circumstances, the environment for this reaction, so takes place at 35 degrees Celsius, anaerobic, so without oxygen, and using a yeast enzyme catalyst. And the reaction for this is sugar turns into ethanol and carbon dioxide. Again, we've got another table here, just some examples of how this will look. So the actual structure and how you'd write it. Then we have carboxylic acid. So ethnic acid is a member of the carboxylic acid, and that's meant to say ethanoic, with the functional group COOH. These four carboxylic acids dissolve in water to produce acidic solutions, so a pH less than 7, react with metal carbonates to produce carbon dioxide, turning lime water cloudy, a salt and water, so when this acid reacts with metal carbonates to produce carbon dioxide, a salt and water, and it also reacts with alcohols in the presence of an acid catalyst to produce esters. So you can see the kind of reaction that takes place to create the ester in the little diagram in the bottom right. And they do not ionize completely in solution, so do not release many H+ ions, so they are weak acids, and so also have a higher pH, less acidic than strong acids of the same concentration. Again, you've got the table here in the top right corner, which basically just shows you how it's written and also how the actual structure of it will look. Then we have synthetic and naturally occurring polymers. So alkenes can be used to make polymers such as polyethylene and polypropylene by addition polymerization. In this reaction, many small molecules, also known as monomers, join together to create polymers. The repeat unit has the same atoms as the monomer because no other molecules is formed in the reaction. Then we've also got condensation polymerization. So this involves monomers with 2 functional groups. When they react, they join together, usually losing small molecules such as water, and simplest polymers are produced from 2 different monomers with 2 of the same functional groups on each monomer. So you can see in the little diagram at the bottom how ethene has turned into polyethene. And this is the way you want to be drawing it. So make sure you definitely have these lines leaving the C through the bracket and also the little N in the corner. And then you've got amino acids. So these have two different functional groups in a molecule, an amine group and a carboxylic acid group. They react by condensation polymerization to form polypeptides. Different amino acids can be combined in the same chain to produce proteins. Then a type of amino acid is the DNA. So this is deoxyribonucleic acid. This is a large molecule essential for life. Obviously, if you study biology, you know how important DNA is. It encodes genetic instructions for the development and functioning of living organisms and viruses. Most molecules are two polymer chains made from 4 different monomers called nucleotides in the form of a double helix. Other naturally occurring polymers include proteins, starch, and cellulose. So that's everything from this topic. Please let me know if you have any questions at all, any feedback or anything, and I shall see you soon. Don't forget to subscribe and like, and all that usual stuff. But thanks so much for watching. I hope you found this useful, and I shall speak to you soon.